Hi everyone, my name is Tae-Jung. I'm currently a postdoc at the UKP lab working on text summarization and conversational AI. Today, I will give an introduction to generation-based conversational AI. So here's the outline. We'll first introduce conversational AI and applications. After that, we then discuss steps for building a conversational agent. First of all, there are two main types of dialogue system, conversational system. So task-oriented dialogue system and open domain chatbots. The categories are divided mainly by their functionality. So as named, task-oriented conversational agents help users achieve some goals or tasks. They aim to complete user requests with the least number of turns. There are three common scenarios of task-oriented conversational agents. The first one is for information consumption, such as weather query. The second one is to support decision-making process, such as he is here. Is it good to go out at 6? Other decision-making process includes suggestion for taking some online courses, book recommendation, and so on. Last, conversational agents help users to complete a task, such as restaurant reservation, airplane booking, and scheduling meeting. Differently, open domain chit-chat aims for free-form conversations and unbound topics. Open domain chatbots are expected to engage users for long conversations. The openness of possible conversational topics makes it challenging to build an open domain conversational agent, as the agent may do well on the topics that have been seen during training, but cannot give a good conversation about unseen topics. So why should we work on conversational AI? There are many real-world applications, including one that we are very familiar with, personal assistants. For example, Siri, Google, Alexa, Cortana, and so on. There are other areas calling for dialogue systems, such as education, healthcare, and customer service. For online education platforms, conversational agents can act as tutors and learning companions to support users, practice languages, provide training, and facilitate discussion. In terms of healthcare, we have chatbots that help to identify symptoms of anxiety and depression through conversations and provide mental health tips. You may have experience with chatbots for customer service. These chatbots usually provide information regarding a particular product and perform actions requested by the users. Here I mostly talk about text, but dialogue systems are not limited in terms of input and even output. The input and output can be text, images, data, or videos. So there are many challenges in building a generation-based dialogue systems, including coherence resolution, conversational discourse, consistent response, diverse response, and factual correctness. We will show you methods that tackle some of these challenges in the next few slides. So to build a conversational agent, we can break it into 4 steps. So first, we need to select the data for our task. Next, we need to select a model architecture to learn from the selected data. Then we train a model on such data. And finally, we evaluate the trained model with different evaluation metrics. So first of all, data. What kind of data can we use for generation-based conversational agents? We can collect data from machine-to-machine conversations, human-to-human, or human-to-machine conversations. So each type has their own benefits and limitations. Machine-to-machine conversations are the easiest data to collect. However, these data are often noisy and unnatural. Human-to-machine data are also available. You can collect from the existing dialogue systems. However, such data only cover a limited domains and usually include bias and noise. Human-to-human data are the most difficult to get. We can only gather small size in some particular domains. So current method usually use human-to-human data from Twitter or Reddit. However, they are kind of forum discussions rather than a real conversation. So building a new dataset for conversational AI is really difficult, and we need to trade off some aspects really depending on what we are aiming for. Next, I will introduce some terms that are used in this field. So each gray box here is a user utterance. It could be a word, a phrase, a sentence, or a short text, as long as it's the input from the user in one turn. A response is denoted in blue here, which is generated by the system. We can use templates or machine learning models to generate a response. In this talk, we mainly focus on the machine learning models to generate a response. Dialogue history includes multiple user utterance and the response, which is used to track the context and the past statements. Next, we'll talk about the model. The basic architecture of our generation-based conversational models can be represented with this simple framework of encoder-decoder. In this framework, the input is the dialogue history, which can be the current user input, an image, or even a video. But in this talk, we only consider textual input. The job of the encoder is to take the input and convert that into a dense vector. And the decoder takes the vector to generate response, which is a sequence of text. So first, let's have a look at the input and output of the encoder-decoder framework. So in open domain chit-chat, the input is simply the dialogue history, and the output is response to the user. Meanwhile, in generation-based task-oriented dialogue systems, input can be dialogue history, belief state, database, or API results, which I will give more details in the next slide. And the output will be response to user. The belief state, given the dialogue history, or a database query or API service to obtain the required information for task completion. So here is an example of input and output of task-oriented dialogue systems. Each input or output is by itself a sequence of tokens. So let me introduce these terms. So first, the dialogue history. It contains previous user utterance and previous generated response. And the belief state is the dialogue state containing domain and of the current conversation, user intent, and the slot values of the whole conversations. The database state is the results returned by querying data from a task-specific knowledge base or API service, and the response, which is first generated by the system, is a lexiconized response. So the lexiconized response is a response, yeah, but the correct name, the correct slot values are masked by some placeholder, such as restaurant name or the value food. The system then will fill these placeholders with the information from the belief state and database state. The user finally will get the complete response. So in task-oriented dialogue, we detect user intent from the utterance and the corresponding slot values. In this example, the intent is 5 restaurants and the corresponding slot values are expensive, Chinese food, and location is the north of the town from the dialogue history. Gather intents and slot values of the entire dialogue history, we get the belief state. This is the first step of the end-to-end task-oriented dialogue model. The input is the dialogue history, previous belief state, and the current user input. The output is the updated belief state. So the belief state is then used to query a task-specific database to obtain the database state. For example, here, we query the database to get restaurants that match the price range, the food, the area requested by the user. The query returns a list of restaurants that match the query. Here, only one restaurant matches the user requirement. So there are 2 other cases of the returned results. One is that no match is found from the database. In this case, the system is expected to suggest different restaurants for the user or ask user to train some slot value. Another case is when there are multiple matches found. The system can either show all these matches to the user and let the user select one of them, or the system can ask user clarification questions so that the user can give more slot values to reduce number of matches. So to generate response, both the belief state and database state are used. Response can be varied depending on the context, but usually in conversational AI, only one response is given, and we only learn to generate such response. So in summary, the end-to-end task-oriented dialogue model generally performs 2 steps. First, take dialogue history as input and generate belief state. The second is after getting database state, using belief state, the model will generate response given on current information. We note that some models try to generate system actions before producing response. A system action is predefined action that the system should react to user given a situation. For example, here, the action could be confirm booking. So in conversational data, some data have a system action annotation, but some don't. So if we want to use the system action, we can either use it as a labels from the available data, or we just use this as a latent variable. So end-to-end task-oriented dialogue system will learn these steps in one unified model for sequence generation. So we have gone through the input and output of a conversation model. Now we will talk about the model. The encoder-decoder framework has been introduced in previous lecture. The encoder takes the input text and produces a context vector, and the decoder then generates the output text given the context vector. We have learned that the decoder generates one word at each time step. Such generation is called an autoregressive generation, as the current output is conditioned on the previous output. So Y2 is conditioned on Y1. A main issue with the autoregressive generation is error accumulation during decoding. If the model generates a bad output at one time step, then the following generated sequence will get even worse. So why don't we generate onwards at the same time? Non-autoregressive generation is proposed to address this in non-autoregressive generation approaches. We first predict the output length and then generate on the target tokens according to the predicted length. The constraint on the output length is the main issue in such generation approach. Another issue is because of the conditional independence of output tokens. Non-autoregressive generation may generate repeated tokens, usually the high probability ones. So far, I have introduced the two types of generation in conversational AI. We mainly use autoregressive generation approach. Here is the generation process of autoregressive generation approach. We start with a special token DOS, begin of sequence, indicating the start of the sequence. So at each time step, the model computes the score of each token in our vocabulary, taking previous generated token as input. The model will continue generating until it produces the end of sequence token, or when the generated sequence reaches the maximum length. So how do we select a token at each time step? There are several decoding strategies for selecting the token at each time step. We will talk about some main strategies that are used in dialogue systems. First of all, the simplest approach is to pick the token with the highest probability. This is called greedy decoding. The output is one sequence with the highest probability at each time step. However, the major drawback of greedy decoding is that it may miss the high probability sequence because it selects the highest probabilities of a previous time step. For example, here, at first glance, we can see that at the first step, greedy decoding will select the highest probability token. Then following that, it will lead to the sequence I have a house. The overall probability of this sequence is 0.08. But we can see that we can go back to the first step. If we choose like as the first token, then after that, we have the sequence I like my cat, which has the higher probability in overall 0.135. So the pick at the first step affects the whole sequence after leading to a sequence with lower probability. So beam search reduces the risk by tracking of n best candidates at each time step, producing several sequences at the end. And then n best candidates at each time step is called beam size. We commonly use 5 or 10. So at the end, the sequence with the highest probability is selected. For example, here we will keep track of 2 best candidates. So we will keep like and have and expand the sequence after that. At the end, we will get the highest probability sequence, which is I like my cat instead of I have a house. According to recent evidence, beam search can work well in tasks where the length of the generated sequence is predictable, such as machine translation, but for open-ended generation, like conversational generation, beam search can vary greatly, but we can use length penalty to somehow reduce the sequence length issue. Another issue of beam search is repeating word sequence and less diverse sequence. So here is a figure comparing the probability of tokens selected by beam search and selected by human. So why beam search select high probability tokens? Human, in contrast, tends to select tokens have much higher variance in the predicted probability. And because of the variance, the sequence is more surprising. So random sampling is proposed to give the surprise to the output. So the first sampling method we consider is the top case sampling, which samples a word from the most likely keywords. So sampling here means that the next token is randomly selected from the set of defined tokens according to its conditional probability distribution. So we know that using sampling decoding, the generation process is not deterministic anymore, as we may sample different tokens from the top K. So this approach is expected to generate more novel and less repetitive sequence. So when the K equal to 1 is the greedy decoding method that we have introduced in the previous slide. And when we increase K, we get more diverse output, but also more risky as we may sample unrelated tokens. So V-n-grams may occur using top K sampling, and the output may not be coherent. And while we decrease K, we get a safer output as tokens occur frequently. But we don't have a perfect solution to choose K. There is no best K that fits on task. So instead of using a fixed K of tokens for sampling that may include unrelated tokens, why not depend on the predicted probabilities to find a set of tokens? So top P sampling is proposed for this purpose. The idea is to select a smallest subset of tokens whose cumulative probability is higher than a predefined threshold. We usually use 0.95 as threshold. So this way, the size of the set of tokens can dynamically increase or decrease according to the next word probability distribution. For example, here, having threshold is 0.95. At the first step, the top P sampling picks the minimum of what exists together 0.95 of the probability. So this includes four words in total. So in the second step, top 3 words total together exceed a total 0.95 probability. And in the third step, only 2 words are considered. So in theory, top P seems more elegant than top K, but actually in practice, both works well and are usually used in combination to avoid low rank words and allow dynamic word sets. Well, despite the dynamic set, top P sampling still may not include surprising words in the candidate set. So in general, all these decoding strategies select tokens based on the predicted probability of the generation model. Although top K and top P samplings are proposed to reduce repeated sequence and produce more surprising response, recent studies show that they still suffer from these issues. So the main cause of this issue is the way a model is trained. So how do we train the model? Let's have a look. In general, the model is trained using maximum likelihood estimation, MLE. So MLE encourages the model to maximize the condition non-probability of target text. This is also called teacher forcing training. However, MLE focuses on maximizing probability of the next token by first sharpens the entire probability distribution instead of minimizing the rank of the next token in a more uniform distribution. Also, it does not optimize the entire sequence, but only the next token at each time step. So frequent words are often predicted, leading to repeated sequence. And any wrong token prediction will lead to error accumulation. And the following generated sequence is getting worse and worse. So a likelihood training is proposed to alleviate the problem by minimizing the likelihood of undecided tokens. So far we have talked about an autoencoder architecture for building conversational agents, and how can we train the encoder-decoder model? But we have not included any attribute that defines a good conversation. So what makes a good conversation? This is a list of several aspects defined by C and colleagues. First, we don't want repeated response by conversational agents. Repetition includes internal repetition, which is repeating words or phrase within a response, or repetition across response as different response from an agent are the same. And last, partner repetition, that simply repeat what the user said. And the generated response is also expected to be interesting. Interesting can be defined by having common sense when reacting to the user, or having knowledge about some discussing topic. Interesting response can also lead to engaging conversations. So the response, of course, should be coherent and fluent. Wrong grammatical or wordy and redundant sequence cause difficult while reading, listening, and sometimes annoying. The response should also be related to what the user just said to bring the feeling of being listened to the user, so the user knows that the system pays attention to them. And conversation is mutual interaction process. So don't expect the user to be the only questioner. The agent is also expected to be inquisitive and ask to know more about the user. In the next few slides, I will introduce some methods to make a conversation better. So let's go back to the encoder-decoder framework. This is a general framework for text generation tasks. So to consider different attributes that make a good conversation, we can modify either the neuron architecture or training setting. So recent methods often initialize the framework based on large pre-trained models, such as T5, GPT, S. This large-scale pre-training helps to generate more fluent and diverse response. Decoding strategies can also help to modify the generated sequence. Top P and top K are proposed to generate better than greedy and beam search. However, in practice, the repeated workflows are still present using these two sampling. We also cannot control the generation towards a target attribute, only using top P or top K. So guided decoding can direct the decoder to generate attribute-related output. We can also modify the input sequence to include the attribute description, or to condition the model on the embeddings of such attribute. Or we can train the model with reinforcement learning, where attribute scores define the rewards. So the large pre-trained model mentioned in the previous slide are trained for generic text generation. It does not include specific bias towards dialogue generation. So several models have been proposed to extend the pre-training to dialogue data. Most of these models use social media data for pre-training, such as Twitter and Reddit. Mina use public domain conversations, but the data and the model are not publicly available. Thoughtbot use 9 task-oriented datasets for pre-training. So all of these models employ transformer-based architecture. And BlenderBot use a poly-encoder transformer that produce multiple representations for a context, and other only have one single representation for the context. So most models are trained by generating response. Each of them has their own additional objectives to improve training, such as latent act recognition that predicts the response action. The response is generated conditioned on the latent variable and the context. So another interesting objective is maximum mutual information. It employs a pre-trained backward model to predict the source sentence from the given response. So more details can be found in this paper. So how can we encourage a model generate towards a predefined attribute? For example, how can we generate response with positive or negative sentiment? To do so, we need to define an attribute model to score the generated sequence. If the expected output should be positive, we resample the sequence if it is predicted as negative by the attribute model. Or we use the loss with respect to the attribute score to train the model. Well, that's very abstractive. So let's have a look at related work on safety in open domain chatbots. So dialogue systems that are pre-trained on large-scale data. These data are gathered from online web on which human users can freely express anything they want without any censor. So such data, unfortunately, may include human bias, and training on such data may lead to toxic response generation. So this will absolutely bring bad experience to the user, and we, of course, don't want that. For example, here, when a person talks to the system that he hacks everyone, the reaction of the system is unacceptable. At this point, the system should try to talk to the person. So can we define a sensitive word list that when we generate the next token, we try to block the model to generate any of these sensitive tokens. We can also add safety classifiers to identify whether the generated response is safe or unsafe. So for unsafe response, we can simply resample another response and repeat the safety process again. Another method is to modify the input to incorporate attribute while training a model. We can add attribute description to the input and train the model to generate sequence according to the description. So common attribute descriptions to the input sequence include style, topic, emotion, personal profile, or situation description. If the attribute is a real-world knowledge, such as from textual word knowledge, from tables, from knowledge base, or some API service, we first need to retrieve such knowledge using some information retrieval methods. And then the results of the retrieval can be transferred into text and add directly into the input, such as the sample here. So here is an example of adding attribute description to the input text. This is the transfer model using GPT architecture for generating persona response. The input includes dialogue history and persona description of the system, and the generated response at time step t. The task is to predict the next token. We note that all the input are in a single sequence. So instead of adding attribute description to the input, we can condition the model on the attribute embeddings. Attribute embeddings can be obtained from two ways. We can train the embedding simultaneously with the generative model, or we can obtain it from additional models, such as clustering or using link prediction models to integrate a knowledge base. So here is another example of personalized conversations. The speaker model is proposed to encode persona in dense vectors that capture the speaker's characteristics, such as background information and speaking style. The speaker embeddings are used in concatenation with the input of the decoder. The speaker embeddings are learned jointly with word embeddings and all other parameters of the neural model. So because of the training of speaker embeddings in response generation, speaker ID close in embedding space tend to respond in the same manner. Here is another example of attribute embeddings for building empathic conversational agent. So an empathic conversational agent is expected to understand the feeling of the human partner and reply them accordingly. For example, here, it's relevant if the boss said, "Why wouldn't anyone promote you?" But it would be too harsh and rude. So here, congrats, that's great, sounds more empathic because it knows the proud feeling of the user, and we should be happy for the user. So the model here, instead of learning specific embeddings to represent the attributes, it learns to predict the emotion of the dialogue at the current time step and generate the response as knowing the current emotion. So we can also define the design attributes as reward signals to learn a model using reinforcement learning. In reinforcement learning, the model takes the current state, which is dialogue history, and previous generated tokens as input and select an action. An action is the next token to be generated. The rewards are often provided by attribute models or it can be some types of metrics, such as similarity scores. So here is an example of using reinforcement learning for personalized response generation. The authors define 4 different reward signals that encourage the consistency between a response and personal profile. The 4 different rewards include personal consistency that expects the generated response can be entailed by the personal facts. And the second is topical coherence, which ensures the similarity between the response and the last user utterance. Fluency and repeated tokens to make sure that the response is grammatically correct and coherent. So we have learned some methods to build a good conversational model. We now see how to evaluate such model. As other natural language applications, we have automatic and human evaluation for dialogue systems. Automatic evaluation metrics compare the generated response with the reference response. So these metrics can be grouped into several categories. The perplexity computes how likely a model generates the reference response. N-gram-based overlapping metrics such as blur and rouge are also used to compute the overlapping words between the 2 responses. So distinct n-gram measures the diversity of the response, which focus on the number of distinct n-gram in the response and penalize response with many repeated words. So these metrics detect only the surface from similarity without considering the semantic similarity. To compute the semantic similarity, model-based metrics have been proposed. Among them, the 2 well-known metrics are BERT score and adversarial success. BERT score computes the semantic relatedness of the generated response to the reference. Adversarial success classifies whether the generated response is machine-generated or human-generated. So a good model is expected to generate fluent and natural response that can fool the classifier. So these model-based metrics are not interpretable and not always aligned with human judgment. Because of the limitation of automatic evaluation metrics, human evaluation is often in combination with them. There are 2 evaluation interactions for human judgment. The first scenario, a person is given a dialogue history, goal response, and generated response for evaluation. The second scenario, the person is provided interactive interface to communicate with a system and then evaluate on the interaction outcome. There are 2 ways of evaluation. First, human judgment is required to give ratings of a model according to some predefined criteria. The second way is to select between 2 given systems given their output. However, human evaluation is known for expensive and time-consuming. Also, people are very subjective. It's difficult to control the evaluation quality of different human judges, as well as a single person and themselves. So generally, both automatic and human evaluation are often used together. In general, there are still lack of metrics for evaluating how efficiently a generation system can avoid generating improper or offensive language. We also need evaluation metrics that can evaluate the generated text based on factual consistency. So factual evaluation is more important than ever in text generation, as neural models can generate fluent and coherent text but may not ground it in the real world knowledge. So we have introduced several techniques that are used to build a conversational model as well as evaluation efforts. There are still many rooms ahead for improvement, and we still need better automatic evaluation metrics that work well. That's it for today's talk. Hope you enjoyed this talk and find conversational AI interesting. Thank you for watching the video.